$1 million Mellon Institute of Industrial Research is formally dedicated. It is now ready to serve mankind, one of the greatest centers of its kind in the world. Laboratories are equipped with ultra-modern devices for the advancement of science. Air hygiene is an example of the Institute's work. Here they study occupational diseases due to air pollution in industrial processes. The dreaded silicosis is fought with the latest weapons, and X-rays aid in seeking its cause and prevention. On the left are good lungs. On the right, lungs affected by 7 years of silica. These the scientists study.
That was the news in 1937. And here are the highlights in the construction of the Mellon Institute building. The story of Mellon Institute goes back to the first years of this century, when Robert Kennedy Duncan, a young chemistry professor, traveled extensively in Europe and was imbued with the spirit of cooperation that existed between industrialists and scientists there. Upon his return to America, he began to advocate that scientific investigations carried out at universities but directed toward the solution of industrial problems would be advantageous for both scientists and industrialists alike. In 1907, he initiated for this purpose a system of industrial fellowships at the University of Kansas. His thoughts and writings about this subject came to the attention of Andrew W. and Richard B. Mellon in 1909. They were so impressed by the vitality of Duncan's work that they invited him to establish a Department of Industrial Research at the University of Pittsburgh. The first fellowship began operation on March 1st, 1911, in a frame building at Thackeray and O'Hara Streets on the university campus. The Mellons not only provided funds for this temporary structure, but also established and sustained research on smoke abatement as an important problem of broad civic need. Following the course of Dr. Duncan's work with close attention, and realizing that the researches were leading to results of considerable value, the Mellons decided to sponsor the programs on a permanent and expanded basis. As a result, on March 1st, 1913, the current institute was founded as the Mellon Institute of Industrial Research and School of Specific Industries, and the first permanent home for the institute on the University of Pittsburgh campus was occupied in February 1915 by the 23 fellowships then in operation. The institute continued its activities as a part of the University of Pittsburgh until 1927, when it was separately incorporated as the Mellon Institute of Industrial Research. The corporate name was shortened to the Mellon Institute in 1962. Through the years, close cooperation has been maintained with the academic community. Most unfortunately, Dr. Duncan died in 1914, but his work was carried on vigorously by his associates. In particular, Dr. Edward R. Weidlein was responsible for much of the growth of the Institute into national and international prominence. He had been a student and associate of Duncan at Kansas, and later an industrial fellow of the Institute. In 1916, Dr. Weidlein was appointed associate director and became its director in 1921. For 35 years, he guided the Institute until his retirement from the presidency in 1956. Soon after the financial depression of 1929, the Mellon brothers commissioned the architectural firm of Jansen and Cocken to design a larger structure to house the growing institute. The instructions to the architects read, "The building must be, first of all, to fulfill its essential purpose, the most advanced scientific workshop that modern architecture, construction, and design can give. It must, secondly, be a building with simplicity and beauty and grave majesty to inspire its delvers in science and the world which will observe it through the years, and to diffuse that dignity which befits a building in which scientific knowledge is to be pursued." To the architects, then, was posed the problem of reconciling two demands that seemed to conflict with each other, the utmost in utility and in beauty. The choice for the exterior was in favor of early Grecian architecture, simple unadorned, of ageless beauty. In order to design a low structure with 6.5 million cubic feet of space, having proportions similar to the Parthenon, a substantial portion of it had to be placed underground. The detail of the exterior was all developed from the small temple of Athena Nike on the Acropolis at Athens, and from the temple at Sardis in Asia Minor. Some of the Institute's features were changed in the planning stage. A scale model, 1/4 inch to the foot, was constructed. The width of the steps was reduced, and much of the Grecian statuary shown in the original drawing was eliminated. A full-scale wood and plaster model of a corner of the building, complete with 2 columns, was erected in a cornfield near Fox Chapel. This led to several changes in the measurements and the deletion of the gargoyles and the remaining statuary. To make room for the present building, the old Lloyd House, which stood on the property, was moved across Belfield Avenue onto the university campus. Temporary laboratories set up in this structure were occupied in January of 1928. The Mellon Stewart Company was selected to be the contractor. Ground was broken for the new building on November 5, 1930. Mr. Harry S. Coleman, former Director of Engineering for the Institute, was at the controls of the steam shovel for this big event. Mr. Coleman worked closely with both the architects and the contractor, and was largely responsible for the many innovations in the design and arrangement of laboratories and facilities. Work progressed rapidly on the excavation. Altogether, about 100,000 cubic yards of material were excavated in 64 working days. Most of the dirt removed was hauled across Belfield Avenue and deposited on the university property. Part of the Cathedral of Learning campus was about 4 feet below street level, and the dirt was used as fill. Sheet piling had to be driven with a steam hammer around the entire excavation to an average depth of 30 feet. The basic excavation was completed March 15, 1931, about 3.5 months from the groundbreaking. This was the largest excavation in Pittsburgh up to that time for purposes of building construction. The water in the excavation was mostly surface water from rain and melted snow. The actual ground water level was just about the first floor level. No rock was hit until the average desired depth of the excavation was reached. After the topsoil, there was a sort of quicksand, then a very plastic clay, and then more sand down to the rock. Nearly 30,000 square feet of sheet piling was driven. To brace it required 40,000 linear feet of timber and 19 tons of structural steel members. All of the drainage ditches, the boiler room, and the holes for the structural steel footings, as well as the elevator pit, had to be cut into the bedrock. Blasting gelatin was used instead of stick dynamite. The gel could be packed right into the crevices, and a neater job of blasting resulted. The protector mat was constructed of 1-inch manila rope lined with strands of steel. That looks like a 2-by-2 foot beam, plenty heavy, but watch it go. Before the excavation could be completed, the sheet piling had to be braced. Structural steel members were used to tie the piling together, and then the timber braces connected. Most of the braces were constructed of 2 lengths of timber. When the main braces were in place, excavation continued down the face of the sheet piling to the depth of the foundation walls. which was a little below the first floor level. Then supplemental timber bracing was put into place. After the sheet piling was all braced and the excavation completed, the forms for the foundation walls were constructed. The timber braces for the piling were not removed immediately. The forms were built around them. The concrete was poured, and then the braces pulled out, and the holes in the walls filled in with concrete. Pourings of concrete started about March 15, 1931. This was one of the first buildings for which concrete was specified in terms of a strength value, say 3,000-pound concrete, instead of a mix ratio. The foundation walls were 20 inches thick and required about 2,700 cubic yards of concrete. Excavation for the boiler room didn't start until all the piling and bracing was in place. Since the boiler room went down an additional 40 feet, the timber bracing at the boiler room pit had to be lengthened continuously during that excavation. Four derricks were used for the structural steel erection, one in each corner of the building. The first steel work was set in around the boiler room about August 15th. Work progressed very slowly, and only the steel framework in this area was completed by October 1st. However, at this time, work was speeded up, and by the first anniversary of the groundbreaking on November 5th, the steel work was completed to the 5th floor in all areas. By January 1932, all the structural steel, grossing about 4,200 tons, had been erected. The basic roof was constructed of reinforced concrete and structural tile. After waterproofing, a quarry tile deck was placed on top. The entire steel structure was fireproofed with concrete. All of the concreting had to be completed before any stone was laid. Since this building was to be used largely as a chemical laboratory, fireproofing was an absolute essential, and the interior construction had to be such as to confine a fire if it did occur. The first piece of limestone laid was a piece of the base course around the walls. The stone was pre-cut at the quarry, and every piece numbered. A special non-staining lime mortar was used in setting all stone. To lift the limestone blocks and all other pieces except the columns, 2 holes were drilled in at an angle with apex toward the center. Then steel pins were driven in and held with a wire pine sliver to reduce the fracture possibility. A release of cable tension permitted the pins to be removed and the lifting rig disengaged. All of the limestone for the building came from the same quarry. Mr. R.B. Mellon was not satisfied with any stone then being quarried, and the Indiana Limestone Corporation opened a new quarry near Bedford, Indiana, from which was obtained a very white stone. The quarry was named the University Quarry, and it was exhausted when all the stone had been removed that was required for this building. Out at the quarry, to prevent sagging of the blocks for the columns, it had been found necessary to cut the blocks roughly 10 by 20 by 40 feet, with the 20-foot measurement, the vertical one, as the block came out of the quarry. The block had then been wrapped in many layers of burlap and kept soaked with water to age over a period of 14 months. The block was subsequently halved, and the hardened stone, supported only at the ends, turned on a lathe to 1/16 inch perfection in diameter. Also at the quarry, the columns and the limestone bases had been turned to perfect level. The cast concrete base on which the limestone base rests likewise had been ground level. These levels had to be true if the column was to be truly vertical. The columns were shipped by rail, one to a flat car, and unloaded at the East Liberty Freight Yard, where the Western Electric Company building now stands in Point Breeze. In unloading the columns, the rope was wrapped around the column 3 times before connecting it to the winch. The column thus was rolled off rather than pulled off, and rope burns on the column prevented. To facilitate handling, each column was fitted with 2 steel bands. Transporting the columns to the building was quite an undertaking. A police escort was required for the special trucks utilized, and the manholes had to be reinforced. Mr. R.B. Mellon took a very keen interest in the entire construction and was constantly on hand. He took particular delight in the columns, and that is his car following right behind the truck. As the columns arrived at the building site, the trucks were pulled in directly under the gantry crane and just opposite the point where they were to be erected. To ensure smooth, safe operation at the construction site, the specific system for handling the erection of the columns had been worked out at the quarry. A special crane was constructed for this purpose. The short leg of the gantry ran on a rail along the top edge of the building. The tall leg, perhaps 80 feet high, ran on a rail constructed at street level to be parallel to the top edge of the building. The steel bands around the column were lined with para-rubber sheet, about 1 inch in thickness, to produce the friction necessary to prevent slipping. That the system worked well can be attested to by the fact that not one chip was knocked out of any of the columns, capitals, or architraves, or for that matter, out of the other limestone pieces. The columns were very carefully positioned by the gantry crane operator, with directions from the men below. 1/4 inch lead sheet was used to prevent the weight of the column from squeezing out the mortar before it set. The first column erected was on the Belfield Avenue side of the building at the 5th Avenue corner, and the last, the one at the rear of the building near Dithridge Street. A column was held in position only by its own weight and the trueness of the level to which it and the bases had been turned or ground. It was just balanced there. The scaffolding around the column was erected only to provide the workmen with a platform from which to operate when they were placing the capital and the architrave. The scaffolding did not touch the column. At first, it took about 2 hours from the time a column arrived at the site until it was in position. Usually, 3 columns were erected in a day, but toward the end, 4 a day were erected. The capitals for the columns and the architraves were shipped from the quarry in a roughed-out condition. The contractor set up a carving yard near the Point Breeze freight station. The firm of John Donnelly and Sons of New York City did the carving, employing at one time 59 carvers. The capitals were handled by the same type of hole lift as the wall stones. Each weighed about 6.5 tons, and they were about 7.5 feet by 5.5 feet. They were moved into position by the gantry crane. Although the limestone work was completed January 1st, 1933, the granite and a great amount of other exterior work remained to be done. As the exterior limestone was being erected, the interior court tile was being put up, so these two jobs were completed at about the same time. The most striking feature of the Institute's exterior is its colonnades. There are 62 columns in all, 18 in front, 16 on each side, and 12 in the rear. These are the largest monolithic columns in the world, and the greatest number used in one building. Each column measures 36.5 feet long by almost 6 feet in diameter, and it weighs 60 tons. There were many delays in finishing the interior. However, this was accomplished late in 1936, and occupancy of the building began shortly thereafter. The building was dedicated on May 6, 1937, with impressive ceremonies, during which Mr. A.W. Mellon spoke.
The building being dedicated today realizes the hopes of many years. I have been very happy to have a part in this work and feel it has been a great privilege for my brother and me to provide this place where men of science can come in their search for new ways to increase the usefulness of industry, to promote health, and so improve the common lot of all. If this institute can contribute, even in small measure toward this end, all of us here today can feel that our efforts will not have been in vain.
The numerous contributions to scientific knowledge, industrial progress, and the public welfare that originated in this edifice since its dedication have amply fulfilled the vision of its founders. Today, many years later, the Mellon Institute successfully continues its comprehensive investigations in the fundamental and applied natural sciences, the training of research workers, and the providing of technical information adaptable to professional, industrial, and public advantage.